Welcome back, everyone. In this video, we're going to start looking at organic chemistry. Specifically, we're going to apply the rules of valence to various condensed molecular formulas, skeletal formulas, carbon backbone diagrams to interconvert between each of those. We're going to review the different classifications of hydrocarbons, including alkanes, alkenes, alkynes, and aromatic hydrocarbons. So, organic chemistry is so awesome. And that's because there are literally millions and millions of different organic compounds, each with slight little tweaks perhaps from each other. Some of them are massive, some of them are very small, but the complexity and the level of detail within organic chemistry being so large is great because it allows us to have such a diverse arrangement of chemicals, different uses, different applications. If we look at naturally occurring organic compounds, there's a protein called titin. It's named that way because of its size, simply. It has hundreds of thousands of atoms within the molecule. It's the largest protein known to mankind. The largest human-made molecule is called PG5. This consists of over 55 million atoms. And if we look here on the right, it is 170 of these structures bound to each other in succession. But that pales in comparison to our DNA. Our DNA consists of organic molecules that are over 100 times more massive than PG5. And so we can see, looking at the difference, titin, which is the largest protein, 3 times 10 to the 6 grams per mole. The largest man-made, human-made molecule is 100 times heavier than that, and our DNA is even 100 times heavier than that. So we're looking at billions of grams per mole, millions and millions of atoms, all combined within these different molecules, or in the case of DNA, our chromosomes. So let's now start talking about how do we classify it? How do we talk about it? How do we interpret organic chemistry? So we've looked already about how we can represent molecules in different ways using the molecular formulas, the Lewis structures, the structural formulas, the carbon backbone structures. And you need to be able to use the rules of valence to convert between the condensed molecular formula and the structural formula. So I will walk you through what this process looks like. But we need to remember that when we are talking about the rules of valence, this is stating the number of bonds that an element will typically form. Carbon has 4 valence electrons, so the rules of valence state that it needs to form 4 more bonds in order to be satisfied. So when you look at carbon and all of the different organic structures, you will see that there are 4 bonds. Sometimes there are 4 single bonds, sometimes there are 2 sets of double bonds, sometimes they're a triple bond and a single bond, or really any combination that gets us 4. So now let's talk about different classes of hydrocarbons. So hydrocarbon, if we break this down, we're looking at groups of hydrogen and carbon. And so hydrocarbons just have carbon atoms and hydrogen atoms. We can have alkanes, which is something that has only single bonds. We refer to this as being saturated with hydrogen atoms. And then we have alkenes, alkynes, and aromatic, and these fall under the category of unsaturated. How to interpret these carbon backbone structures? Just remember, each point represents a carbon atom. So this has 6 carbon atoms, and then it has the number of hydrogens needed to satisfy the valence. So we have 3 hydrogens on the leftmost carbon because it only has 1 bond and it needs 3 more. 2 hydrogen atoms on the second because it has 2 bonds to carbon and needs 2 more bonds. And then we repeat that process all the way through the entire molecule. And so we can see what the total molecular formula is of this. We have C6 with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 hydrogens. So you need to be able to do something like that. And then repeat that process for these other molecules. So actually, why don't you pause the video now and see if you can determine what is the molecular formula for these remaining structures. Welcome back. You should have determined that for this alkene, we have C6H12. The alkyne is C6H10. And the aromatic hydrocarbon is C6H6. The one that's probably the most difficult here, if we look at the alkene, these each are 1 carbon. So we have a total of 6 carbons. The alkyne can be a little bit difficult to see. You need to make sure you're counting the carbons that are at the ends of those triple bonds. And then the 6 carbons here on the aromatic hydrocarbon as well. So let's now delve more into alkanes. Alkanes have a general formula of CnH2n plus 2. So for an N value of 1, this would be C1H 2 times 1 plus 2, or CH4. We repeat that process for the different N values, and you get the molecular formulas that are listed. Each of these, we could draw their Lewis structures. And you need to be able to go from the condensed molecular formula to the Lewis structure. So something to notice here is that because hydrogen only ever forms 1 bond, it's always going to be attached to the carbons. And the carbon forms what we call the backbone. So anytime you see the condensed molecular formula, you should see a line of carbons that are bound to each other. The 3 carbons here, the 4 carbons here, and the 5 carbons here on pentane. So you should be able to see the connections between the different carbon atoms, that they each have a single bond. Then you put on the remaining hydrogens to satisfy their octet. Now, you also need to be aware of and able to use the names of all of the first 10 alkenes. So the prefixes, hex, hept, oct, non, and dec, are modifying our ending, which is ane. And the ending ane comes from the term alkane. So what we will see later is that when we look at alkenes and alkynes, if we wanted the alkene version of hexane, that would be hexene. And if we wanted the alkyne version of hexane, that would be hexyne. So the prefix tells us the number of carbon atoms, and the ending tells us whether we have an alkane, an alkene, or an alkyne. So let's practice here. To which class of hydrocarbons does each of these belong? And then also determine which of these are saturated. Remember, we talked about saturation in terms of whether or not there are hydrogens on the molecule, or rather how many hydrogens there are. So pause the video and try and answer these on your own. Welcome back. All right, let's see if you are able to determine the correct answers. Our first molecule has a carbon-carbon triple bond. That's an alkyne. Our second molecule we see has alternating double and single bonds. From earlier videos, you should know that that means that this molecule has resonance, and this is an aromatic compound. Our third structure has no double bonds, no triple bonds, doesn't have any, the ring, while there is a ring, it does not have alternating double and single bonds. So this is just an alkane, and we're going to call this a cyclic alkane because it's in a circle, it's cyclized. D has 2 different sets of double bonds, and we call this an alkene. And now in terms of saturation, all of these are unsaturated because they don't have the maximum number of hydrogens that they could have based on the carbons. Now, A, B, and D should make sense because we see that they have double bonds or triple bonds. Therefore, we've replaced those hydrogens with a double bond or a triple bond. The cyclic alkane, however, might be a little bit more of a struggle for you, and we're going to come back to this in a little bit. So put a pin in that hat, and we will come back. Let's look more at alkanes again. So applying what we've learned from chapters 8 and 9 of the ebook, we know that the carbon atoms are going to have a tetrahedral geometry, and that's because they have 4 bonds, either to carbons or to hydrogens. The bonds will point into the vertices of a tetrahedron and have a bond angle of 109.5. Because of the single bond, which we know are sigma bonds, these bonds are able to rotate about each other. And so we can represent the chains as these zigzag type structures, where these the carbon atoms are free to move. So for octane, we can actually draw it in a variety of different ways. These are just 2 different ways. We could also show it kind of scrunched up, or kind of forming again, we can have all these different arrangements, and that's because the molecule is able to rotate and move around because it's got free rotation due to the fact that there's no double bonds constraining it. We can also look at molecules in their straight chain form or their branched forms. So octane can be written as a straight chain. We also call that N, or normal octane, or as a branched molecule. This is isooctane. And the different structures will lead to different properties. We'll explore this more when looking at functional groups and when looking at intermolecular forces. I've put a link here, another video that you should watch that helps you to visualize the fact that alkanes are free to rotate. I wanted to put this slide in here to point that out to you and let you know that there's that additional video for you to watch. And this will help you to see that, in fact, this molecule here, this is just one molecule, hexane, drawn in different ways, but these are all identical to each other. We also have used a little bit of this notation in the past, where we have dashes and wedges, and these indicate the directionality of the bonds. The wedges are coming out of the screen, and the dashes are going into the screen. Remember, when we look at a tetrahedral shape, we know that it's 3-dimensional. And so we know that we have kind of that tripod, if you will, with the one atom sticking out on the top. And so we need to have 3 dimensions, and we depict that by using the dashes and the wedges. Let's now dive a little bit deeper into those cyclic alkanes. So if we take hexane, C6H14, and we can see that it's free to rotate around. However, we can form ring structures as well. If we take that same number of carbons and we form a bond between the 2 ends, we now have formed an additional carbon-carbon bond, and so we need to remove one of the hydrogens on each of the carbons. That gives us then, for the ring structure, the basic formula of CnH2n. And so there are different ways of representing cyclic molecules. This is what we refer to as chair notation. And when you take organic chemistry, you'll see more about that. We can also have smaller rings, cyclopentane, cyclobutane. And so what we see is that we can have different ring structures of different sizes. They will therefore have different shapes. and also different stabilities, as we'll talk about a little bit later. But what we notice then is that forming a ring structure is what we would call a point of saturation, similar to what we saw already with the double bonds and triple bonds. All right, here's the last question here for this video. So what I'd like you to do here is draw the Lewis structure for each condensed molecular formula that's on the left, and then also draw the Lewis structure, or rather determine the molecular formula for the skeletal structures. So you want to determine the Lewis structure for the molecules on the left, and then the Lewis structure and the molecular formula for the molecules on the right. Pause the video and try this on your own. Welcome back. So let's see what you were able to do. This first molecule shown here. Remember, as you are trying to relate the condensed molecular formula to a skeletal structure or to a Lewis structure, you want to keep in mind that the carbon is kind of our backbone here, and the other elements are going to be bound to it. Second molecule, carbon, bound to nitrogen, 3 different hydrogens, and then the nitrogen has 2 hydrogens. Did you draw the lone pair of electrons on there? I hope so. You should have recognized that nitrogen needs them in order to have a satisfied octet. This third one, we can see 2 carbons, a chlorine, and then another nitrogen. Remember, chlorine being a halogen only forms 1 bond when it's not in the center of the atom. So we have a carbon with a carbon, and then the nitrogen. This carbon here has 3 hydrogens. And this carbon has a hydrogen, a chlorine, and then the nitrogen. And the nitrogen has 2 hydrogens. And be sure that you include the lone pairs of electrons on chlorine and nitrogen. The last molecule here on the bottom we have a carbon, carbon, carbon. So we have 3 carbons. That forms our backbone. The carbon on the left also has a bond to hydrogen, and then oxygen and hydrogen. Now that one might have been a little bit more of a challenge for you, but you should recognize that this comes in a set in order to have the correct bonding pattern. If you tried to draw a bond from this hydrogen to that carbon, then the carbon will either have too many bonds or the oxygen wouldn't have enough bonds. The carbon in the middle is bound to 2 fluorines. Make sure you include their lone pairs. And then the carbon on the left is bound to bromine, chlorine, and fluorine with their sets of lone pairs. Okay. Here, you should have gotten C4, H8O. This is C4, H8, C6, H14, and this one, C2, H3NO. Now, in this case, as long as you got the right number of each element, it doesn't matter if you put them in a different order. Finally, how can we classify these molecules? Pause and see if you can classify these as alkanes, alkenes, alkynes, or aromatic. Welcome back. So all of these molecules on the left here, these all have carbon-carbon single bonds. So these are alkanes. This is a cyclic alkane. This is a regular alkane. This is an alkene. And this is an alkyne. Okay, that's it. Thanks for watching. Have a great day.